Hello, my friend, and welcome to this new recording. So, as promised last time, we're not going to jump into the implementation of the compute pipeline into the Nervland engine. So, also, yeah, I'm now trying to use my headset to do the recording because I think the sound with the camera itself is not as good. So I'm planning to get another microphone for the camera, but until I get this one, let's try with the headset. I think it could be a little bit better. So let's just jump into the topic right now. So for the implementation of this compute system, I decided to go with the same kind of structure that we already have for the render pass and the render node. So actually, I started with the render pass class itself, and I just made a copy to create a compute pass, and I basically remove most of the content that you have for the render pass. The thing is, a compute pass, or actually everything concerning the compute pipeline in WebGPU, is you could see that as a very simplified version of what you can do with the render pipeline. Basically, it will allow you to do some processing on the GPU, but you don't really have to deal with the concept of a vertex shader on the first part and then forwarding everything to the fragment shader, and you don't have to consider the depth filtering, the blending with the fragment target. All this stuff is really for when you do rendering. So when you do just computation on input and output, you don't have to consider that. In fact, if you just focus on the render on the compute pass itself, a key difference is when you set up a render pass, you need to specify what is go or what are going to be your targets. Where are you going to render something? And when you get to the compute pass on the opposite, you don't have anything like that because your compute pipeline is going to do some processing on some inputs, and it can actually write something to also provided outputs, which are going to be storage or texture outputs, but they don't really have to be well specified at the level of the compute pass itself. Actually, you don't specify them there, which means that in a single compute pass, in fact, you could have a first pipeline which is going to accept a bind group targeting a first texture if you want, and you would do rendering into that texture. And then just after that, you could have another pipeline targeting another texture thanks to another bind group, and then again another pipeline targeting maybe a buffer this time, and you're going to write data into this buffer. So you can have different targets in a single compute pass. At least that's how I understand it so far. I must admit I haven't really tested everything, so maybe I'm wrong. You never know. Anyways, let's just have an overview on what we have exactly in this compute pass. So first, another interesting thing is when you have to create a compute pass, normally I would specify some details, some construction information in a structure, but it turns out that this structure is completely empty for the moment because you don't have to specify anything to create a compute pass, which is not completely true because there is something concerning some timestamp, I don't know, and I'm not really considering that for now. So you can just provide some default for that. Anyway, if you compare that to the render pass, render pass. You quickly see that for the render pass, we already have quite a lot of information that we can pass to customize the construction of the render pass itself. But here it's not the case. Apart from that, what we are also keeping is the ability to set up an encode handler. This is similar to what we have already in the render pass. And the idea is you could specify a function here that is going to, well, handle the encoding of this render pass, part of the encoding at least. So if we go into the encode function actually, so you have it here. This is executed when it's time to use a command encoder and write this compute pass in the command encoder. So with the command encoder, you're going to begin the compute pass. And so with this compute pass encoder, then you want to define what are going to be the computation you want to do. So you may still have here this encode handler function, and you would provide that with the compute pass encoder. And I don't know, you could do specific stuff in there, but currently I'm not really using that yet, so no real example for that. Apart from that, let's move to the next part that we kept. So we definitely need an encode function, which I've seen. Another thing we still have is the ability to set up specific preprocessor definitions. So these are you then when it's time to build your actual compute pipelines. So whenever you want to, well, take a compute node which will contain a compute pipeline, and you want to integrate this compute node into this compute path, the compute node will receive those definition that we have specified for the path itself, and it's going to use those definition to build the pipeline with some modification maybe into the shader code itself, because those preprocessor values are forwarded to the shader code and they are applied in the code. So yeah, you can still define that on the pass level. And then the other key thing is this one. You can add what I decided to call compute steps into a render pass, because as I said, whenever you have such a pass, you can have multiple dispatch of work one after another actually in the pass, and for each of those work dispatch operation, you could set up a specific pipeline and you could add specific bind groups, and then you would define what is the dimension of the work that you want to perform. So all those information are now contained in this compute step. So this is a simple structure which is going to tell you what are the dimensions that you want to use for the compute operation to do, then what is the pipeline that you're going to use, and what are the bind groups that you're going to use. When it comes to the bind groups, there's a small additional trick here, but it's the same trick actually as what we have in the render pass. And as you see here, we have a special structure which is a dynamic bind group bind, and this one contains a regular bind group, but also it may contain a vector of dynamic offsets that you want to use when binding this group, because if you have dynamic offsets for one buffer or maybe two buffer or whatever, some entries in this bind group, you may want to use those dynamic offset and specify them to use well, different offset for those different entries in the bind group. So when you have a vector like that, You are supposed to specify the offset for all the buffers that are dynamic in this binding. So yeah, this is a generic way to handle this consideration if you want. And that's all you have actually in the compute step definition. And you can basically create a list. You have a vector of those compute steps. So you can add multiple of those steps into compute path, sorry. And then when it comes to encoding the compute path, sorry, when it comes to the encoding part, we've seen that there's maybe this encoder function, but then the key thing is really this part to automatically handle all those compute steps. So you would actually iterate on those steps, and you then try to figure out in a kind of optimized way, because if, for instance, you have a first step setting up one pipeline, and then you have another step where you're going to use the same pipeline, you're just going to change the bind groups, then you are not going to call set pipeline again. I guess it's probably not making a big difference, but not being very sure about it, I decided it might be good to just optimize that and avoid setting the pipeline if it's the same as the previous used pipeline. And we do the same actually for the bind groups. But for the bind groups, you have an additional layer of complexity because you may, for instance, be using the same bind groups as for your previous compute step, but you could be using different dynamic offsets for those bind groups. So you have to consider equality of the bind group itself and also equality of the dynamic offset. And if it's not the case, you just try to reassign everything. So here you reassign your bind groups. And after that, you're going to dispatch the work using the dimension of the current step that you have. Doing this for all the steps that were registered in this compute path. And finally, we also have this additional element now where you can just add a compute node into the compute path. And what this is going to do is pretty simple. You are just going to collect all the compute steps that were defined in the compute node, also taking into consideration the compute preprocessor definition, which I mentioned before, because this may actually change the behavior of the pipeline, which is defined in this compute node. So yeah, this is it for the compute path itself. Then, as I said, we also did the same thing for the compute node, and you have here a simplified version of what you could get actually from the render node. I started again from the render node and trimmed everything down, keeping only what was relevant for the compute version of it. So what do we have in there? So when you start building a compute node, you have a node base. Yeah, this is something I also introduced in the process. Trying to find a common base class for the compute node and the render node, and this is what I call the node base here. And this node base is going to contain now the builder that we have for the bind groups, because this part is something that you have in common for both the compute node and the render node. When it comes to defining a bind group, except that no, you don't really have defined bind group at this level, because defined bind group is going to be a template function, so, and it's going to return your current class, so you can't really define that in the base class. But anyway, yeah, you have also this add defs, which is a command element. And so what do? We have the possibility to create a pipeline again, but this time it's going to be a compute pipeline. We can add some bind groups, add some definition in there also. We can bind everything with this template function here. I think I'm not really using that yet. And then you have this part where you actually can add some work to do. In the render node version, we actually have a few different ways to add a model that you want to draw, to add a draw call directly specifying the number of vertices you want to draw, but with no vertex buffer. You can draw, if you provide a model name, it's going to set up everything for you. You have support for indirect draw calls also like that. So you have a few options here. But for the compute node, it's much more simple. Basically, whenever you want to add something, it's going to be a compute step. So you want to specify the work dimension, as we do here. You want to specify what are the bind groups that you want to use. And optionally, you may want to specify dynamic offsets into those bind groups. And that's all, because the pipeline part, this is provided by the compute node itself. When you define the compute node, at start, in fact, when you create that, you're still providing the name. Where's my constructor? Oh no, I mean, yeah, it's here. So you still providing the name of the shader that you're going to use for this node, and this time it's going to have to be a compute shader, which make me think of something. We'll get back to this later. Anyway, whenever you call this, as you can see, I have two versions here because there are cases where you might not want to specify any dynamic offset if there is no dynamic buffer. So whenever you call that, you're going to define a compute step, but at first you don't have a pipeline assigned yet. So we set that to null. And you add your bind groups, taking into account the dynamic offset in this case, and you just keep this compute step in a list, in a local list. In the other version, you're just going to do the same thing, except that when you're creating the bind group, you're not specifying any dynamic offset because you don't have any. And then when it comes to add this compute node into a compute path, at that time you know exactly what are the preprocessor definitions that are available from the render node itself, because in the compute, I said render node, sorry, from the compute node itself. So in the compute node you can still add definition like that. And so you have this available, and you also get the compute definition from the render path itself. So all of this are combined together, giving you the list of preprocessor definition that you want to use to compile the shader to build the pipeline. So it's only at this time that you can build the pipeline, taking those compute definitions into consideration, and that is going to produce your compute pipeline object. So then you just iterate on each compute step. You actually make a copy of it here. Maybe we don't, I guess, yeah, you're just emplacing that, so making a copy. And at this point you set the pipeline, and you just add that to the list of compute steps that was provided as argument here. And this list comes from the compute path itself. You can see here in the compute path, we're collecting all the steps in the internal member. And this is it for the compute node. Not much more to do with that. So that's it for the basic implementation of those two elements. Actually, there were a few additional steps. I think I mentioned that in the description here, creating those two things, but then you also need support for creating an actual compute pipeline in the WebGPU engine. And yeah, that's it basically. You need the compute pipeline builder class itself, but this one was also not really tricky. So this one is similar again to the render pipeline builder. It's going to allow you to specify the layout, the shader you want to use, and so on. So this is used internally in the compute node to effectively create a pipeline. And starting with this, I decided to set up a minimal unit test. And this unit test here is trying to perform a very simple operation using a compute pipeline. And actually, the reference I use for that is this page, which I have up in here. And this is a very simple demonstration of how you're supposed to set up the compute pipeline in WebGPU. And we're going to go through basically the same steps, but encapsulating most of the stuff because we have a higher level interface already. So what we have here is simply starting with creating a compute path. As I mentioned, we don't need to specify anything for the creation because there's no real parameters to provide here. And then we are setting up a compute node with some code. And yeah, in fact, this is another extension I just introduced in my system. Normally, when I set this up, I need to specify a file here. The file should contain the WGSL code. But I thought that when it comes to unit testing, I don't really want to have to create an additional shader file every time I need to test something like that. So it would be good if I could just provide the actual code itself directly as a string here. So I have simply added support to check for this prefix now. And if this is found in the shader file name, it's going to consider that this name is actually just the code directly. So it's not going to try to open any file, and it's just, well, removing this prefix and using that directly as the code. I could show you maybe where this is done. Oh, come on. If I can remember. Yeah, I have introduced this function to unveil that. And this function is the one doing the job. It's going to check if you have this prefix. If it's the case, just removing the prefix, and otherwise we're going with the file opening process. So we're just creating a compute node here with some code. As you see, the code itself is very minimal here. We have a first bind group, and in this bind group, we're defining two bindings. The first one is going to be an input buffer, which is an array of float with 64 elements, and the second one is going to be an output buffer this time, and it's storage, which is tagged as writable. So this is the output where you can write content. And this are coming directly from what we have in the simple code here. I think I've seen that somewhere, probably. Yes, this part. And when you have those resources available, you have a very minimal function here, which is going to use a global invocation ID, and using this ID to multiply the input by 2 to store the output. So what do we do next? We have this input definition. And now I have here what I call a GPU Buffer Proxy. In fact, this GPU Buffer Proxy, I mentioned that in my notes. Probably at the end. Yeah, because I've modified that a bit lately. At some point, I think I mentioned that in the previous recording, I had this dynamic buffer system. So I introduced a dynamic buffer base class as a base for the dynamic buffer, but without any kind of template parameter. And later on, I also introduced a GPU buffer as a base for the dynamic buffer base. And the GPU buffer just provides you some kind of wrapper around a WebGPU buffer. And so different utility function using this buffer. While the dynamic buffer base kind of encapsulate that, the GPU buffer, but additionally also provide you with a CPU version of the content that you have in the buffer. So it's providing a vector containing unsigned SHA data with the size of the buffer. So you can actually map the CPU data to the GPU data, and you can actually update the GPU data from what you have written on the CPU side using this class. But I thought that dynamic buffer base was a bit of not so cool name if you consider that this is a class that you can use on its own. And eventually I decided to rename that to GPU Buffer Proxy, which to my mind makes sense because this is providing you an access to the GPU buffer that is encapsulated and allowing you to bridge the CPU copy with the GPU copy. So this is exactly what we have here, the GPU Buffer Proxy. And when you build that, you just specify, okay, the number of elements that you want. Alignment of the element should be most of the time either 0 or 1 here. 0 being used only if we want to use dynamic offsets and you want to space the content using the appropriate offset for the buffer, which is 256. And then you specify the size of each of those elements. So in this case, since we set the alignment to 1, it's going to be a continuous buffer, in fact, of float. So you have 64 floats straight in the memory. And you use that as storage. So storage means read-only storage in this case. I mean, you don't really have to specify if it's read-only or not read-only at this level. Then you also have an output buffer, which is the same kind of idea, except that it's not even a proxy because you don't have any CPU mapping for this GPU buffer. Everything for the output is really just on the GPU and you don't have access to that. That's where you're going to do the rendering from your compute pass. And except if you try to download that on the CPU, you don't have any kind of mapping. But the point is, you actually can't even download that on the CPU side because a buffer which is planned to be a storage buffer like that is not allowed to have this map read flag. So that's why we actually have another buffer here, which is a staging buffer we're going to use to retrieve the content of the output. And so for the first one, the output itself, we are going to add this flag, the copy source, because once we are done with the compute pass, we are going to copy the content of this output buffer into the staging buffer. So the staging buffer also has this copy destination flag. Then what do? We just start with the input. We retrieve the pointer to the data on the CPU side, and we fill that with actual data we want to use. Then we update this. So this is actually sending everything on the GPU for the buffer corresponding to the input. Then we continue with the compute node here, and we define a first group, which is the only group that we have actually. So the group 0 here, and the group 0 contains first an input buffer. So that's what we can provide here with as sto, so as storage if you want. And then the output, which is a read-write buffer. So we are just providing read-write storage. So this is for the definition of the bind group layouts. So then you actually need to create one of those bind group using this layout as a template. So you do that just after here, create bind group, you use the layout for the group 0 here, and you just again provide the actual buffers this time. These are actually the same calls, but they're not doing the same thing. And this is going to create a bind group, and then you just add a compute step. So in this compute step, you have to define the dimension that you want for your step. What we have to take into consideration at this level is the group work size that you use in the actual compute shader. So here we use 32 elements for the X dimension of the work group size. The Y and Z dimension are set to 1 by 0, so you have actually 1, 1. It's the same thing like that. So if you have 32 elements per work group, how many work group do you need, knowing that your buffer contains 64 elements? So you need to perform 64 computation, but these are grouped by a group of size 32. So you only need 2 executions. So this here, you provide the number of work group that should be executed on each dimension. So again, this is similar to 2, 1, 1. So we can just specify 2, and then you specify the list of bind groups that you want to use. And in this case, the list, which is a vector, contains only a single element, which is a group 0 we created just before. And when this is done, you can already create the pipeline, assuming there would be no compute definition coming from an arbitrary compute path on top of that. So that's not really how you want to do in, at real time, but you can test that, and it should be a valid pipeline already in our case. And then when we call this add function into the compute path, then this is where the actual pipeline would be created. It would be recreated if the compute definitions are different, or otherwise it's using the previously computed version if there's no difference in the preprocessor definitions. So yeah, and at this point you actually take the compute step that we defined just before from the node, and you introduce that into the compute path. And then I am setting up everything to submit the computation. So you get a command builder. In this command builder, which is basically encapsulating an encoder as far as I remember, probably. So you request the execution of this compute path, and after that you request a copy from the output buffer into the staging buffer with 0, 0 offset using the full size, and you submit that. Then I have also introduced a very handy system on the GPU buffer class, so you can have now this read sync function. Probably we should provide some details on that at some point, but yeah, this recording is already too long. Come on. So let's just bypass the details. With that, you get access to the downloaded data from the GPU, and you can just iterate on that data then to check that it's indeed twice what you were providing in the input in the input buffer here. And that's it. when you execute this this unit test, it's working just fine, no error, so everything is all right. What did I change here? Nothing, right? Okay, so yeah, this is it for the first overview on this introduction of the compute pipeline support. As described in this DevLog article, the idea is really to try to use all the compute pipeline now in the elevation producer, trying to replace what I was planning to do with the render pass. So we'll see how this is evolving shortly. And yeah, this is a part where I add some details on how to use read async and the read sync function, but yeah, I don't have time to discuss that further. So anyway, thanks for watching. See you another time, and until there, happy coding on your side. Bye bye.